Hi, I'm Emily. I'm from 771, and in this video series, we'll be designing a robot drivetrain in Solidworks CAD. From this series, you'll learn all the skills you need to CAD anything else after this. In addition, I will also be including some mechanical design tips, branching off of the mechanical lessons on the website. In this video specifically, we'll be designing the frame of the drivetrain, and in the rest of the videos, we'll be continuing with the rest of the assembly. And for reference, this is the style of drivetrain we'll be following. It won't look like this exactly, but this is the style. It's called West Coast Drive. So let's get started. Let's start by talking about how we're organizing our parts, because as you'll realize, your project folder will fill up with a ton of parts, and it will be pretty hectic to navigate through unless you have an organization system. So this is your project folder. I've named it Drivetrain because that's what we're building, but you should probably name it like 2019 Robot or Off-Season Robot. Within the project folder, we have these subfolders for how we should organize our parts into. And for any mechanism-specific parts, we put them within our mechanism folder. So everything should have its place. So yeah, our mechanism also includes drivetrain, which is what we're building today. So we just have a drivetrain folder, and we will put stuff like our belly pan in there, our drivetrain gearboxes, etc. into that. So let's get CADing. This is Solidworks. To start by making a CAD file, we're going to click New. There's three options. Drawing, we don't have to worry about. That's more for manufacturing and showing other people how to manufacture your parts. For actual, like building actual CAD files, you're going to be using either part or assembly. The difference between the two is that assembly is just made up of parts. So we're going to start by making a part. And eventually you use both of them together. Or as in parts, and then you move to put your parts into an assembly. So to make our parts, we start with a 2D sketch. So go to the Sketch tab, enter Sketch, and we sketch our 2D stuff off of a plane. So I'm going to choose the front plane. And what we're making right now actually is VersaFrame. So the 2x1 VersaFrame. And you don't have to make every single part. Anything on Vexpo, you can pretty much download the CAD file, as well as other FRC suppliers. But for convenience of showing off CAD skills of sketching, as well as convenience for us when we're editing this material, we are going to make it ourselves. And you will see why it's a good thing to make it yourself. So, oh yeah, and the only other thing you have to remember when you're making VersaFrame yourself is just that the maximum length you can order online is 59 inches. So just don't make VersaFrame that's like 60 inches. So anyways, you pick a sketch tool up here, and there's also drop-down menus for each one. I'm going to start with the center rectangle, and we build off of this origin point. So I'm going to click there and like that. If we weren't building off of that point, let's say I just did this over here, then I can move this around and move it like that. And ideally, we don't want to move around any of our stuff. We want it to all be defined. And as you can see right now, I can move this like that, but I can't move it along there because it's stuck to this origin point. So I'm going to dimension that using Smart Dimension, making it 1 by 2 inches. There we go. And you'll notice how the sketch is now black and that I can't move it. When it turns black, it means it's fully defined. So that's a good thing. You also notice these dotted lines versus the solid lines. The dotted lines don't affect your sketch or your part. The dotted lines do. They will edit the shape of your sketch and your part, or yeah, they will affect the shape. These will not. These are more just for reference. Okay, so now we have the outside of our VersaFrame. We're going to create the inner wall happening there. So we can create a new rectangle and dimension that, but that would take a while. So we can use this handy tool called Offset Entities. Click our shape, and you can see how it's outlining a rectangle around ours. And we can edit the distance between that. I'm going to leave it at 0.1, and I'm actually going to reverse it. You can also make it bidirectional too. We don't need that right now though, so I'm going to click yeah. And I am ready to make this 3D. So I'm going to exit my sketch, go to the Features tab. Also make sure your sketch is highlighted, so otherwise it would look like that. Highlight your sketch, and click Extrude Boss Base. So you can see, I drag this out, yeah, I can make this 3D from my sketch. And I can also edit the dimension here. There's also other methods of how you're extruding your part. I'm just going to go with blind though. And I want this to be just 1 inch, a 1 inch block. I'm happy with that. A 1 inch block of VersaFrame, that's what we're going for. And now I'm going to create the holes going along the side. So I'm going to create another sketch. I'm going to sketch using the top face of this part as my sketch plane. So I'm going to choose a hole because we're making holes. You'll notice how this dotted line shows up, and that's because it's suggesting I make a reference. Or sorry, it's suggesting that I make a relation. So right now I can still move this around, but I do want to make it vertical. So how do I make it vertical? This is one method. I can select the point here, the midpoint, and sorry, that's a secret menu, I'll get to that later. I'm going to search add relation. So I have that point selected, and select this point. I'm going to make it horizontal, and you can see the other options here. But I'm happy with horizontal. And now, I can't move it side to side, I can only move it up and down. That thing that I pulled up earlier, that's a shortcut menu. If you press S, you can access it and you can customize it with whatever tools you want. So I can just easily access that add relation tool because it is very handy. So anyways, I want to define this into position. So I'm going to use Smart Dimension again. So I can define the shape of our circle. I actually do want to define that. I want to make that 3/16 of an inch. That's just a hole size. And the whole size of VersaFrame, I believe. And I'm going to make that 1 inch away because that's how far away the hole is on VersaFrame. And yeah, now I have one hole. However, I do want to do something a little bit confusing right now. I want to make 100 of these holes, just going along there, like literally 100, because it doesn't really matter. But I'm going to make 100 holes, and I'll show you why. But first, I'm going to show you how. So I could do the same thing. I could just draw out a ton of holes and dimension them. That's going to take a while. So I'm going to use linear sketch pattern. So I am going to make just a line of these holes going to the right. So I'm going to click Entities to Pattern, click my circle. I don't want it to go up, so I'm going to make the x-axis along this line. And I am going to, they're 1 inch apart. I want it to go right, so switch the direction. And I'm going to make 100, because I can. And you can see how that just keeps going on. So I'm going to say, yeah, there's the little 100 number. And I'm going to cut these holes through my material. So it's like a reverse boss extrude. I'm going to go use extruded cut. And same thing with extruding our thing. I can state exactly how far I want it to cut, but I could also just say cut through the entire piece. So I'm going to go with that. And I say yeah. And you can see my other holes. If I go back to the edit sketch, you can see that my other holes are cutting through non-existent material. That'll be handy for what we're doing next. Let me also just save my part right now. And I'm going to save it into stock. Also, before we continue, it's important to add materials to your parts because it will help you keep track of the weight of your robot while you're designing it in CAD. So it's not a surprise on bag day. So how we do that is we can edit the material here. First, let's find out what material VersaFrame is by scrolling down to the bottom. 6061 T6 aluminum. So go here, right click, edit material, and under aluminum, 61 T6, okay, apply it and then close. And you can see it's been applied there. Cool. So now it has the properties of that, and that will always be handy for later. But yeah, now we're going to move into configurations. So if you imagine when building your robot in real life and in CAD, you're going to have many different versions of VersaFrame of different lengths, of the same stock, but of different lengths. Like I'm going to have 5 inches and 10 inches. And when I'm designing this in CAD, I can make a ton of VersaFrame files, like separate files. Like this one's going to be 5 inches. I'm going to make another one that's 10 inches, and so on and so on. But having all these individual files is going to make my project folder incredibly messy and big. So instead of doing that, I can contain all of these within the 1x2 VersaFrame file under configurations. And configurations are just like different versions of the part. So this will be our default setting, this 1-inch block of 1x2 VersaFrame. I'm going to create a new configuration for our drivetrain length. Drivetrain length. And yeah, the question is now, how long do I make it? Going to the 2018 game manual, the maximum dimensions were 33 by 28. Remember, this is our, kind of what our chassis will end up looking like. So I want this to be 33 by 28. This piece, however, is going to have to be 2 inches shorter than the entire length. Like, let's say I want this to be 33. This piece is going to be 31 because this material will add on an inch here, and an inch here. So just keep that in mind. So 33 by 28. So this is the length. The maximum it can be is 33. And I want to be close to the maximum, but I don't want to go over. And this is a tip. Just make your lengths shorter than the maximum, 1 inch shorter, because what will happen is you'll manufacture it, and it's likely that you'll cut it a little bit off, and then it'll be a little bit over the maximum length, and then you'll have problems with inspection at competition. And you'll have to file it down. It'll be a bad time. So prepare for that in advance and just make it shorter. So if we want our entire length to be 32 to be safe, we're going to make this piece 30 inches. So yeah, go here, Boss Extrude. We're going to edit this feature, and instead of 1 inch, we're going to make it 30. Like that. But if we scroll down here, I want to say that this change is going to only happen to this configuration. So I select that there. So now I have this, and look, those holes that we made earlier are pulling through, and they're cutting through this material. So that's what that was for. So now we can look at this versus what we had before. And now we want to make the drivetrain width too. So that was going to be 28 maximum. So we're going to cut off 1 inch and make it 27. So we're going to make a new configuration off of default. Drivetrain width. Okay. And I'm going to do the same thing, 27. And down here, once you click this configuration in that part, it's going to just default to that. So that makes it really handy. And now we have that. Blah and blah. Cool, so I'm going to save that. And what we can do now, just to help us start visualizing it, is making this into an assembly. So, warning in advance, my assembly is doing something kind of weird and I need to fix it. I have yet to, but I will. So ignore what's happening here. This tab is normal. What's not normal are these parts, so I'm just going to delete them. I don't know why it's like this or why they're here. And you'll also see that it's in like this kind of file. I'm going to put it back into assembly. That's what it should be. And this is our drivetrain assembly. Ooh, whoops. This is our drivetrain assembly. So just go ahead and name it drivetrain and save it into the project folder. Cool. So now let's put in our VersaFrame. And we can choose the configuration down here. So let's start with the width. So the first piece you put in your assembly is fixed. And I can't move that around. And pretty much you're building everything off of this and referencing everything off of this. So that piece right here is that piece right here. Whoa. So now let's add in the length piece. Kind of like that. And you'll notice with this one, I can move that around. So I want to reference it. So I'm going to say this piece should be touching here. And I can select my mate type here, but I'm going to go with coincident. And I want this to be on the same plane as this. So I'm going to put it there. So how far away do I want this piece to be from here? Our wheels are going to go in between here, but we can also just use another reference, which is how we'll be fastening the VersaFrame together. So we're actually using, I'll keep that reference up. We're actually going to be using gussets, and Vexpro makes these to pair with VersaFrame, so it's very convenient, and they make a whole ton of different stuff. We're going to be using VersaChassis gusset. So I can download a CAD file of this down here. And I am going to, I'm going to open this in downloads. And this is in a step file. So pretty much step files can be converted into a CAD on any platform. So we're going to make it a Solidworks specific file. We're going to drag that into there. This is our piece, our boy. We're going to save it and save it into our folder as well. To gussets. I'm pretty happy with this name. I like to keep the part number with the name of the file, so it's just easier to find if I need to. So I'm going to save it like that. Also, before we continue, I'm going to specify the material. On here, it is 5052 aluminum. Okay. I don't know exactly which 5052 one is, so I'm going to just go with that one. And I'm going to put that into our drivetrain. I'm going to mate it to be on top of there. And what you should do is, I'm going to call it smart mating. So there's a ton of different ways you can mate a piece to another piece. There's several ways you can go about it, but try to use as little of specific reference points. For example, if I want this gusset right here along these holes, I can make it mated to this hole and this hole. However, like if I needed to change something in the future, this is going to be more difficult to change than if I did mating this hole and mating this parallel to here. Let me do that right now. So let's say I wanted to move this hole over to another hole. All I have to do is delete that hole and then move the gusset over and then mate it to another new specific hole. Does that make sense? Let me demonstrate it. So I want to move this one hole over. I can go to my mates here. It's coincident there, but I want to delete this one. And that's the only thing I have to delete to move it over. Otherwise, I'd have to delete this hole, and then move it over. It also, if you didn't mate it coincident from here to here, then it also slide around that way. So it's just smart mating. Yeah. So I'm actually going to mate it right here, I think. Roughly around there. Cool. And I'm going to mate this to here. Cool. Starting to look like a drivetrain with a singular gusset. And I can do the same thing. I can import in this part and import in that and then do all the referencing again. Or I could just mirror it across. So I have to create a plane for it to mirror across. So I'm going to stick this plane right in the middle of this piece. And I know this piece is, click that, and I'm going to use the measuring tool. This piece is 27 inches. So I'm going to make my plane 13.5 inches. And I could say 13.5 in here, or I could also do 27 divided by 2, because you can do calculations in Solidworks. So that plane is over there. I want it in here, so just flip it to reverse the direction of it. And there it is, right in the middle. Now I'm going to name that plane. I'm going to name that the vertical plane, because I'll be mirroring things vertically, my drivetrain. It's like a vertical mirror, and that's exactly what I'm going to call it. So actually, let me select that, and then mirror. So now it's selected, and I'm going to click mirroring these parts. And I'm going to do the same thing here. This piece is 30 inches. So let me make a plane in the middle of that. And this will be our horizontal plane. I'm going to name this vertical mirror as well. So let's mirror this, this, this. There we go. Cool. Looking a little familiar. And just to double check, let's make sure this is 32 inches. Nice. And then we know this is 27. So we're within our maximum dimensions. Okay, so now I'm going to cut out the holes for our 3 pairs of wheels and our 6-wheel drive. And in this drivetrain, I'm going to be using a method called drop center. So what is drop center? With our drivetrain, our front and back pair of wheels are going to be normal. They're going to be aligned through the center of our VersaFrame. So with our 2-inch VersaFrame, they're going to be 1 inch from the top. Our middle wheel, however, is going to be slightly lower than our front and back pairs of wheels, like an 1/8 or 1/16 lower. What this does is, if our robot is driving in the forward direction, our robot is going to rock onto and lean on the front 4 pairs of wheels. So it'll only be driving on these front 4 pairs of wheels, and our back pair of wheels will be slightly in the air, but not making contact with the ground. Same thing if our robot moves in the reverse direction. Our robot will be leaning on the back pair of wheels, and the front pair of wheels will be up in the air. So at any given point, there are only 4 wheels in contact with the ground. By using this method, we're mimicking driving with a shorter drive base, which helps your robot turn easier. This is achieved through reducing the amount of turning scrub or resistance to the turning power of your wheels. How we reduce this is by, with our short drivetrain, reducing the distance to the center of rotation in the drivetrain. Versus driving with your drivetrain at full length, the distance to the center of rotation is much larger, which will increase the turning scrub. Following the equation, turning scrub or scrub torque is equal to the frictional force on the wheels times the distance to the center of rotation. So we're playing with that last value to decrease the value of the scrub torque. Okay, so let's get started. So we know our middle wheel is going to be slightly lower, so let me start with that. We're going to draw a center line from the center of the piece, and we're going to set this to 1 inch plus, we'll do 1/16 of an inch. Okay. And we're going to make a circle here, and that is for our bearing block. So we're using these gearboxes for our drivetrain because this gearbox has the equipment to be easily mountable to our style of drivetrain, the West Coast drivetrain, following the West Coast Drive gearbox kit. So you'll see in this drawing how there's a bearing block right there, and that bearing block goes through the material, as you'll see in the later video. But we can find this bearing block if we search bearing block here. And if you scroll down to drawing, it's right here, gearbox bearing block. So because this goes through our material, we have to make sure we have a hole big enough to fit it. And we have the hole right here. So the diameter of it is 1.5. 1.5 plus some clearance, and 0.003 is the kind of rule to follow to add clearance. So whatever you have, you add 0.003 as a total to add clearance to whatever you're putting through the material. And then we'll add these mounting holes at some point later, if I remember. But yeah, when you make a drivetrain, make sure to add those 2 holes, or you can just match drill it. Okay, so now we have our center hole, and the gearboxes are going to be mounted on this hole, 1 gearbox on this piece, and then a matching gearbox on the matching opposite piece. But yeah, we have our gearboxes, and we have to make the holes for the outer wheels. But to connect the gearboxes and the motors to those outer wheels, we use methods of power transmission. So this can either be belts and pulleys or sprocket and chain. For drivetrain, it should be chain or 15 millimeter pulleys, which is the thicker pulleys, and belts. But for our situation, we're going to be using chain just because it works with the gearbox we want to be using. So we hook up the chain from the middle where the gearboxes are to the outer wheel in the front, and then another link of chain from the center to the outer wheels in the back. And with chain actually stretches. So to use chain effectively, it always has to be tight. Same with belt, it always has to be tensioned and tight. But because chain stretches, we need to be able to constantly retension it. So actually in a drivetrain, you can pull the sprockets further apart to tension the chain. So this center wheel where the gearboxes are, that's going to be fixed because our bearing block is fixed. And with our outer wheels, we're going to mount them to bearing blocks that we can slide around so that we can move that sprocket, the outer sprockets, further apart from the center, and make the chain tensioned and tight again. In mechanisms, you're not going to see this as often. You're going to see more of this method, just because it's more space efficient compared to the drivetrain. Yeah. Okay, so the outer wheels are actually going to be mounted on these bearing blocks of this image called the Versa block. These bearing blocks actually clamp to the material, and you tighten it using the bolts that you can see. And then, of course, to move it around, you loosen the bolts, slide the bearing block to where you want it, and then tighten it again. And the cam, which is the shell-looking thing next to it, that's to prevent it from sliding one way. You can basically place a cam in front of it, and this has a growing diameter, so that the further you move your sprocket out, you can turn it so that it kind of reaches it. But anyways, those are just to prevent it from sliding inwards. So we would put it on, if the gearbox would probably be on the left side of this bearing block. So we stretch the bearing block, the Versa block out, and this cam prevents it from sliding in to loosen our chain. So we're going to be using this. And this piece, actually, I went down to drawings and then I pulled up this one. This piece has unique center distance from the top of the part. So in one orientation, it's 0.94 inches, or 0.94 inches from the top of the piece. And if you flip it the other way, it will be 1.065 inches. And that's because you can use this piece for a drop center, like you have the outer wheels with the flat top of the block, and then your center wheel can be the dog ears, is what we call them on SWAT, the dog ears on the top, to give it a drop center. And I think that's like a 16th, maybe an 8th of an inch drop. But yeah, we're actually not going to use that, but we are going to be using the flat edge on top, so we're going to be using the 0.94 inches from the top for our outer slots. So let me just draw that now. Center line from the top. And yeah, using construction geometry, because this is just our reference, 0.94. Okay. And then from this point, we want to draw a slot. And we can do that right here. Center point straight slot. Cool. The radius and diameter of the slot just has to be big enough to fit our shaft, because if we look at the bearing block again, unlike our center bearing block, the block isn't actually going through the material. It clamps around the outside. The only thing going through the material is our hex shaft. So that looks like this. The shaft stock. That looks like this. We're actually going to be using this one. So that's the only thing going through our material. And the diameter of the shaft is 0.5, so half an inch. So this just has to be bigger than half an inch. And the radius just has to be bigger than a quarter of an inch. So let's make it 0.35. Let's make this. This is just the amount of sliding room you're giving your shaft. Let's make it 2.5 inches. Or maybe just 2 inches. It's fine. So typically at this point you want to think, what do I need to make the center to center distance of my sprockets with my length of chain that I need? In the drivetrain, you don't really need to be thinking about this, because you can slide your sprockets to make the chain nice and tight. But in your mechanisms, you do need to be thinking about this if you don't have slots. So just like the simplest method is by using a chain calculator or sprocket to sprocket distance calculator. So it just looks like this. If you just Google sprocket center to center distance, this calculator will come up. So we'll actually do that today just to demonstrate. There are two types of chain you'll see in FRC, number 25 and number 35. 35 is just for higher load applications, so it's stronger than number 25 chain. It is also heavier, so try and use number 25 chain as much as possible. If you think your robot's going to be very violently driving, or just you want to play it safe and you want to have it really, really reliable, use number 35 chain in your drivetrain, but you can get away with number 25 chain. So we're going to be using number 25 in our drivetrain, and we're going to be using, let me just pull up the sprockets. We're going to be using 18 teeth sprockets. So they look like this, but this is 22 tooth. We're going to be using the number 18 half inch hex bore sprockets. So we're just going to put in our calculator 0.25, that's our chain, 18, 18. What's our current center distance? If I wanted it right here, wanted our slot right here. Let's find our current center to center distance. Okay, so right now our center distance is 12.55. Let's actually add in pretend wheels, just so we know where our wheels would be. And with our supposed strategy, our made-up strategy right now, we're seeing our wheels are, or need to be 4 inches for the game. Actually, don't do that. If you can, minimize the amount of dimensioning you actually need and do as many relations as possible. So that's just getting the practice. And I forgot to make these construction geometry. Okay, there. So if we have our wheels right here, then it's going to be like that. I'm just going to put one at the very end to see where our wheels could also be, just to make sure that they're not outside of our perimeter. So our distance would have to be much smaller. Also note that the line that I drew to measure the distance between that and there. You could use Smart Dimension, but in this case, I just want to be very accurate, because also note that the center hole is not on the same level as this slot. Remember, it's like a 16th lower. Also, this is a little bit higher, so it's maybe like an 8th, I think. Anyways, yeah, they're not on the same level, so just want to make sure the distance, sprocket center to center distance is correct. Otherwise, it'd be going from like where it would be level. So let's actually try and make this like 11.5. Okay, so 11.5 actually looks pretty good. Maybe like 11.75. That looks even better. Okay, let's try this. Current center to center distance is like 11.75. So good. Our number of links is a whole number. If you notice, I put like 11.33. It's going to give me a decimal, a number of links with a decimal. We want to avoid that decimal number because you can't have fractions of links. So just make sure your number, 25 is just a multiple of your number. So 11.75 is good, and we're going to go with that. Okay, so now let's mirror this to the other side, and you can use the mirror tool. So we're going to select the entities we want to mirror. Let's mirror these wheels in the slot, and then we're going to mirror it about the center line that we've created. So yeah, and then we can extrude cut these. We're going to just go through all. And there we go.